Today we have the graph problem. So given nodes with connections, we have to answer some queries. So let's look at the description. So we have C nodes, for example, 5, and we have connections between them like this, maybe like this, and this graph can be disconnected. So it can be two connected parts or more, or just one. And we given the queries with each having some type, 1 or 2. And for query type 1, we have to answer if the value that's in this query, if the value is online or offline. If it's online, we have to return this value. And if it's offline, like this, we have to look at this group and find the minimum number in this group. For example, this can be 4, 2, 1, 4, and the minimum number would be 1, so we have to return 1. And for query type 2, we do it offline, turning these nodes offline. So it goes offline. So what's the strategy to solve this particular kind of problems with connectivity and queries? So let's first explore how can we do this kind of connection exploration. So we give an array of connections A, B, like this, where each nodes is one is A, second is B, and this a connection. And we have some more of this kind of connections. So one way to solve it is you have to just do exploration. So you can have hash map from one node to all its siblings, like list. Or another solution would be to use union find or disjoint union set. Union find. So we know how many nodes we have. We have C nodes. So the union find with size of C. It's data structure that represented by the array, and each cell initially has the value of its position, like this. And this represents the position of reference. And when you connect the nodes, for example, you want to connect nodes 2 and 5, you go and explore the root of this node. Basically, you have to go to the link. Initially, both of these nodes have the root of itself. So you just go and find the root of A is find of 2, and the root of B is find the relation of 5. Then you modify this link. You can just blindly modify it, like you don't find of root A equals root B, or you can have some optimization, like looking for the rank of this, you don't find tree. The rank is basically how many nodes it has, or you can do a path compression. It is optimization of the find operation. So basically, if you have some nodes that has long path and they eventually go to some route, you can make some link go directly to the route like this, and this would be the path optimization. So the union find answers the question in what group this particular node A is. Basically, the group is the root of the node. The next, we have to answer our queries. So they ask us to find the minimum value. That means we have to use some sorted data structure. It is not possible to solve it with just sorted array because we are doing offline operation, and after that we have to find the next minimum. So I used a TreeSet because all our nodes are unique, and TreeSet has support of removals and finding the minimum node. So basically I do this grouping after I connected all the union find nodes, and this group B is making the hash map of the root to list of values. So if the operation is offline, I go into the group of this node and I do the removal from the TreeSet of this node. Basically, you will never return this node again because it is offline. And when the type is 1 for query, I retrieve my set, and if the node is in the set, it is online, I return the node. And if it's not, I return the first or minimum value. Or if there is nothing to return, I return -1 as in this example. So that's it for this problem. It's medium difficulty, and this solution is you have to first add all nodes to the union find. It is O of n, time and space to add to the union find. Then in each group you have the TreeSet, and in the worst case we have every node in the TreeSet in a single group, and this gives us nlog n time complexity. And for queries, each query has this remove operation, or like, yes, the remove operation is logarithm, checking if node in the set is O of 1, but for binary tree, depending on the implementation, can be logarithm 2, but I think this is O of 1 and the first is O of 1, so the worst case is logarithm. And how many queries we have? It's also 10 to the power 5. So basically the entire algorithm is nlog n time complexity and open space.